Hi guys, this lecture is all about flux. The associated reading is listed here, and the learning goal is to have a good conceptual understanding of the flux of an E field through a surface and why we calculate it the way that we do. Flux can be used for a lot of different types of flows or fields. In general, it's just how much stuff, that stuff could be a lot of different things, is going through a surface, okay, or some kind of opening, something that I can describe with a surface area, okay. In general, the flux depends on a few different things. The first would be the strength of the flow or field. Okay. It also depends on how big the surface is that you're measuring the flux over. So that would be the area of the surface. Okay. And then the last thing it depends on is the angle between the surface and the direction of the flow or field. So there's lots of different ways you can think about flux. You can think about it in terms of fan blowing, in terms of water going through a hose. I kind of like thinking about it in terms of something more fun. Okay, so imagine that there is money falling from the sky, and of course you want to collect as much of that money as possible. Well, what you really want to do is have the maximum amount of flux coming into some kind of container that you're catching the money in. So let's say you're catching the money in just a regular bucket. Okay, if you want the maximum amount of flux, obviously you're going to pick the bucket that's biggest, that has the biggest surface area of the opening. Okay, you're going to want to be in the part of your flow of money where the money is falling down with the most rapid rate. Okay, that would increase the amount of money going into your bucket over a period of time. And then the last thing is, you're going to align this bucket so that the bucket is directed perpendicular to the flow of money, right? Because you want the most amount of money coming into your bucket. Okay, so that way of thinking about why that maximizes the flux works just fine. Okay, it is a little bit trickier to think about flux when you're thinking about, instead of you're thinking about an actual flow of a substance, thinking about an electric field, but it essentially works the same way. So if I think about some different scenarios for an electric field, what I want to think about is the density and the direction of field lines passing through a surface. That's fun. I'm going to draw a little surface here. Okay, this is a little surface. We're looking at it from the side. Okay, I can describe the angle of this surface in space with a vector that is normal to the surface. I'm just going to call that the area vector. Okay, and if this area vector is parallel to the direction of an electric field, then we have a situation that is maximum flux. Now we've got max flux in terms of measuring the flux of the electric field through that surface because our area is parallel, okay, to our electric field. Okay, so one way to think about this is this area here, or this surface, is intersecting lots of these field lines. Okay, if instead, I'm going to copy this, if instead I had a surface that had the same surface area, but it was tilted at some angle, now my area vector is pointing in this way. Okay, now this particular surface is actually going to intersect fewer of the field lines. Okay, like for example, it's going to miss this one. This one clearly caught that one. Okay, so this is a weaker flux. Just like there'd be less money coming into your bucket, there is less field intersecting with this area. We'll just say not perpendicular to E. And then of course we have a situation of zero flux, and that's when we've got our surface area here totally perpendicular, okay, to the electric field. When I think about actually passing through the surface that's defined by this vector that's normal to it. None of these electric field lines are passing through that surface. It would be like turning that bucket sideways, and no money is actually coming into that bucket. So this would be a situation of zero flux. So as we talked about in 183, we can have a really simple situation, okay, if the vector field, in this case, the electric field, okay, which means both the magnitude and the direction of it are constant across our surface, okay, then we have a really simple situation where the flux is just going to be equal to the dot product of that electric field and that area vector. If these guys are parallel to each other, then you just end up getting the full magnitude of the vectors times each other. Okay, that's just how the dot product works. If you need to review that, there's some stuff in your book that's useful. And you can also, of course, look online or in an older textbook. Okay, of course, that's a little bit too easy for what we're doing here. Sometimes, right, we'll have that situation, but we want to have a more general equation. So if the vector field, in this case, we're talking about an electric field, but we can make it even more general than that, is not constant. So either the direction or the magnitude is changing, okay, across your surface. Then you want to break your surface into a bunch of little pieces, right? Okay, and again, this should be familiar, hopefully, and that's okay if you don't remember, from 183, but right, I can break this surface then up into a bunch of little surfaces. I'm going to pick a different one so you can actually see what I'm drawing here. So I'm going to pick this little surface here. I can draw a vector that's normal to that little patch of surface. And if I make that little patch of surface small enough, then I can assume that the electric field is constant over that little patch of surface. And then all I have to do is sum up the flux through each little patch of surface, okay, to get the total flux through the surface. That would be the same thing as taking the sum over all those little elements of the electric field dotted with those little surface elements. Okay, that looks just like this, except for now we're talking about little infinitesimal surface elements. I'm sure you guys know where we're going with this. We don't want to just do that. We want to take the limit as these little surface elements, the area of them go to 0, which gives us, of course, a integral. And this is a surface integral. Okay, so we're going to integrate our electric field over a surface, and the electric field here is dotted with the dA, the infinitesimal area vector of that surface. Okay, so I want to remind you guys here, this is the dot product, so don't forget about that. That's not just a regular old multiplication sign. And this is what we call a surface integral, okay? When you're doing a surface integral, you want to make sure that the units make sense. So the units of this particular little area element, sometimes you're going to want to use Cartesian, sometimes you're going to want to use spherical or cylindrical coordinates, but whatever you replace this little guy with, it needs to have units of area, okay? So that's length squared. We're talking in this class about the flux, not just of any vector field. We want to understand the flux of the electric field through a surface, okay? So we're going to use the capital phi for that, and that's going to be equal to a surface integral of the electric field dotted with, okay, those little infinitesimal elements. So that's an important equation to remember. Okay. And like a lot of things in this class, doing this integral can, for any kind of general thing I can come up with, weird surfaces that exist in everyday life. Obviously, doing this integral can be quite complex. But in this class, we're going to use symmetry and some nice simple electric fields to make it fairly easy.